So this is 5.1, day 3. We're just going to do a little bit more work on doing our derivative of the natural log function. So a couple things to remember here up on the top, that the derivative with respect to x of the natural log of a function of x is equal to 1 over that function times its derivative. Equivalently, u prime over u. Now sometimes doing that directly leads you into a big mess, and it's usually the du dx that gives you a mess. So for example, if I were just doing this one at its face value and using that rule, I would say that y prime is equal to 1 over u times the derivative of u, which would be the chain rule and give me a negative exponent. Then I had to do the derivative of the guts, and it wouldn't be very fun to do the derivative with respect to x of, and I'm just going to call that u, and then to clean it on up. So what's easier a lot of times is to make use of the natural log, actually all log, the logarithmic properties. I'm just going to write props. And remember what those are. That multiplication expands into addition. Oopsie. And division expands into subtraction. And one of the biggest ones is that powers can come out front. So when you use those properties in conjunction with our derivative of the natural log rule, it becomes a lot easier. So the easier way of doing this one is to write y as x squared plus 2x minus 3 to the 1/2 power, ln. Because what that allows me to do is bring that 1/2 out front. And now I've taken the ugliness out of the derivative of that inner function there. Because now when I take my derivative, my constants don't do anything. I do 1 over u times du. And I could factor a 2 out and cancel it with the bottom over here. I'm just going to write dot, dot, dot for that one because I don't really want to continue writing it, but I'm just going to go dot, dot, dot. So again, with number 14, if I were to do that directly, I'd have a quotient rule going on when I do the derivative of u with respect to x. And I can make this a lot easier if I just take y and rewrite it as ln x squared minus ln 3x minus 2. Because then when I take its derivative, I just go u prime over u. U prime over u minus u prime over u, and I would be done. You wouldn't be required to get a common denominator with that. So nice and easy. So I think for a lot of these I might just break them up for you and then let you use your natural log property. So for this one, again, before I start, I'm going to take this multiplication and expand it into addition. And that's actually 3x minus 1 to the 1/2 power, which can come out front. Now when I do my natural log rule, I get 1 over u du, which is just 1, plus 1/2, 1 over u du, which is 3, or equivalently u prime over u. And I just get 1 over x plus 3 over 2 times 3x minus 1, and it works out really nicely. Whereas if I didn't use those properties, it would get much messier. I'd have the product rule in there with a root, and it wouldn't be very fun to take the du dx if I did this directly as 1 over u du. All right, so number 16, I'm just going to expand it out. Keep in mind it's this whole thing. So you got to be careful with parentheses when you're using your natural log rules because it's the whole thing to the 1/2, not just the top or not just the bottom. So when I expand that y, I have 1/2. And then I also have a division which expands into subtraction. But you have to be really careful because as I have it written, it would only be considering the 1/2 going with the ln x squared, plus 1. So make sure you launch that into a set of solid brackets because it's the whole thing to the 1/2 power. And then you would do your y prime. And I can't stop myself from doing it. I'm just going to have to do it. It'd be 1/2 of 1 over u du minus 1 over u du, or equivalently, u prime over u. And I would finish that one off. I could probably take the 2 and factor it out and continue, but I'm not going to finish that. Now, I'd like you on number 17, if you're doing this via video, to pause the video and just see if you expanded it correctly. I'm not going to finish it. I'm just going to do the full expansion. So I would suggest that you pause the video before you move on. All right, so for this one, when I'm expanding it, the first thing I would do is notice that I have a division splitting the 2, and I would expand that into subtraction. And I'd have ln of x, the top, minus ln of the bottom, which would be 2x squared plus 4 to the 1/3 power. So first and foremost, I have a numerator and a denominator, and I'm going to split those up. The next thing I'm going to notice is that this one's a product, and it's going to expand into addition. Furthermore, my power gets to come out front. And same here, power gets to come out front. And now I would apply my derivative rule for the natural log function, and I would continue. So it's only once I get it all expanded that I actually go take the derivative. That one would be a nightmare to do without the expansion. All right, now this process also is going to rear its head in other contexts. Implicit, relative extrema, equation of tangent line. We approach them all the same way. It's just that within them, we are going to have to be doing the derivative of the natural log function. We're not going to do this. I did it in your notes yesterday, and it's not on the AP exam, but I like it. But we're just going to have this work here kind of filtered down the page. So on the first one, if I was trying to figure out what y prime is, because that's my goal, this is implicit, so I take the derivative of the left-hand side with respect to x. I'm going to write that out nicely. And equals the derivative of the right side, and the derivative of a constant is 0. The next thing I would do is take the derivative of each part of the sum and difference separately. Keep in mind it's with respect to x, so if I have a variable match, super. The derivative of x squared is twice x. Minus 3. The derivative of ln x is 1 over x, but the derivative of ln y is 1 over y, y prime, or dy dx, or 1 over u, u prime. Remember, y is itself a function of x, so we've got to be careful when we don't have that variable match that we're doing the chain rule. Same here. The derivative of x squared with respect to x is twice x, but the derivative of y squared is 2y times the derivative of the guts. So remember, when we're doing implicit differentiation, our goal is to solve for y prime. I need to gather them all together and factor it out. Well, what's irritating me is this y on the bottom. So what I'm first going to do is multiply the entire equation through by y to get that to cancel. And I'd get 2xy minus 3y prime plus 2y squared y prime is equal to 0 times y. So I'm multiplying both sides of the equation here by y to eliminate that. Now I'm going to keep everything that has a y prime in it over on the left-hand side of the equation. And I'm going to move the one that does not have a y prime in it over to the right-hand side. I'm now going to factor y prime out, and I think I like to write this as 2y squared minus 3 instead of negative 3 plus 2y squared, although it doesn't matter. I just think it's more visually pleasing. There we go. And my goal was to find the derivative of y. So what I've got is negative 2xy over 2y squared minus 3. Now, in order for me to actually get the derivative or the slope of the tangent line, keep in mind this is called implicit. It's with respect to x and y. I would need a full point, like maybe at the point 1 comma 4 or something that's on, I don't even know a point on that function. But notice my process for implicit didn't change. I just within there had that natural log rule that I needed to apply. So a lot of the stuff in this chapter you already know how to do. We just have a couple new rules. I already should know how to find relative maxes and relative mins. They occur where the derivative of a function changes sign, or equivalently where a function goes from increasing to decreasing or decreasing to increasing. Now, when we're doing the algebra, in order to figure out where the derivative changes sign, we need to figure out where it's 0 and make a sign line, or where it doesn't exist. So the formal definition of finding relative extrema is to find where the derivative changes sign. And if I'm looking at a graph, that's all I look for. However, when I'm doing the algebra, I really need to find where the derivative is 0. So first thing I need to do is take a derivative. It's 1 over u times the derivative of u, or equivalently, u prime over u. So my derivative is 2x plus 4 over x squared plus 4x plus 6. I want to find my critical values, which is where the derivative equals 0, to determine if there's a sign change there. When you have a fraction, the only place the derivative can be equal to 0 is when the numerator equals 0. The denominator tells us any place where the derivative maybe doesn't exist, but however, this denominator exists for all x. So I don't have an issue there. All right. So what I've got is, where does 2x plus 4, or 2 times x plus 2, equals 0? And that would be when x is equal to -2. This supplies me with my only critical value. It's the only point that could possibly be a relative extrema. It's the only place where there could possibly be a sign change in the derivative. So I'm just going to run a test on my derivative and stick -2 into the function. Now, the denominator is always positive because, well, that's not necessarily true. So anyway, I just go run a sign test, and I'm going to go to the right. And the easiest thing to put in is a 0, and that would give me a positive. It'd be positive over positive. And then I'm going to go to the left, maybe put in a -3. And that's going to give me a negative over a positive. So I've just determined that I indeed do have a sign change in the derivative. Furthermore, I know it's a relative min because the function goes from decreasing to increasing at that critical value. So I would say that there is a relative min of, and in order for me to figure out what it would be, I'd actually have to go plug that back in to the original function. The relative min would be ln of 4 minus 8, it would be ln 2, I think, if you plug that in. That's the min of ln 2. It occurs at x equals -2. I'm just going to make sure ln 2 is right here. I'd do -2 squared, which is 4, minus 8 plus 6. Yep, ln 2 is the relative min. And there is no relative maximum. All right. You should actually go graph that on your calculator to see what the function looks like and see a bottom out over at ln 2. All right, the next one, we've done these a lot. Number 20, find the equation of the tangent line. It requires a point. Got it. And the slope at that point. So again, we've done this question a ton. We've just never done it with the natural log function embedded in our definition of y. So y prime would equal 8x minus the derivative of ln x, which is 1 over x, basically times 1. Now what I need to do is figure out what's my derivative at the point 1, 4. And this is explicitly given in terms of x, so I really only needed the 1 on there for the derivative. It would be 8 times 1 minus 1 over 1, which is 7. So now I've got my slope, and I've got my point, and I'm ready to write the equation of my tangent line. Y minus the y I know is equal to the slope there times x minus the x I know. And I can just leave that in point slope. So today's worksheet is worksheet 5.1. And you will be doing all of that. And the key is posted as well in Edmodo. So have a good one.